Welcome to the sixth session of the third module. In this module, we shall study about the second chapter that will deals about the refrigeration and air conditioning systems. So basically, let us take individually the refrigeration. Refrigeration is nothing but the art and science of maintaining a defined space or volume at a temperature lower than the surrounding temperature. The device which is used for this purpose is the refrigerator. Refrigerator is nothing but a device that is being used for maintaining or making this refrigeration more effective. This refrigeration is useful in preservation of foodstuff, medicines, high precision industries and air conditioning systems, etc. This refrigeration and air conditioning is used to cool products, in order to maintain the temperature lower than the surrounding temperatures, and also in a building environments also. Okay, the refrigeration or air conditioning systems transfers heat from cooler low energy reservoir to the warmer high energy reservoir. Some energy has to move from lower energy level to the higher energy level. So this is very important, that this movement of energy from low level to the high level requires an external energy and an external consumption of external power. Is it clear? Now that is being dealt with one of the thermodynamics law, wherein which the lower temperature reservoir, that is, if you can consider, this might be the refrigerator inside the space, and the outside space it may be high temperature reservoir. So in such cases what happens? The heat from the lower energy level has to be taken out. That means we have to work on the refrigeration system. So the blue color one, which shows that is the amount of heat that has been absorbed, and the red color one, which tells us the amount of heat that has been rejected. Is it clear? Refrigerants that are especially a selected substance that have certain important characteristics, including a good refrigeration performance, low flammability, and low toxicity and low compatibility with the compressor lubricating oil. With compressor lubricating oil providing us a good metals and good heat transfer characteristics. They are usually identified by a number that relates to the molecular consumption. Is it clear? So that is what we call it as the refrigerants. Refrigerant effect can be defined, a few terminologies here like this. A refrigerant effect is also termed as the amount of heat that is being absorbed in the refrigerated chamber per unit mass of the refrigerant. More refrigerating effect means less mass of refrigerant that is being required. The ton of refrigeration, it is defined as the capacity of refrigeration system, which has been expressed in tons of refrigeration, which is the unit of refrigeration. Now that is the reason why when you go and purchase the refrigeration or air conditioning system, it is always by 1 ton, 1.25 ton, 1.5 tons, 2 tons. That is how they will define it. A ton of refrigeration is defined as a quantity of heat that is being absorbed in order to form 1 ton of ice in 24 hours when the initial temperature of water is at 0 degree centigrade. That is nothing but ton of refrigeration. Then what do you mean by ice making capacity? Ice making capacity is the amount of ice produced per unit time. It is nothing but an ice making capacity. And one of the important factors is the coefficient of performance of the refrigerator. Basically, this coefficient of performance of refrigerator is the ratio of heat absorbed in the refrigerated chamber to the work input to the compressor. Is that clear? So this is once again it is given by COP, that is coefficient of performance, is equal to heat absorbed divided by work input. Similarly, COP, as the name itself indicates, it is a measure of performance of a refrigeration system, or it may be an air conditioning system. It is similar to the efficiency term associated with any work developing a device. Efficiency or COP can be closely defined as the ratio of output to the input. In a refrigerator, the output is the desired effect, that is the coldness, which is the heat absorbed in the refrigerated chamber, and input is the work input to the compressor, that is what is the amount of electricity that we are supplying. It's the amount of power that we are supplying for that. Relative quotient of performance of refrigerator, it is given by the ratio of the actual COP to the theoretical COP, is known as relative coefficient of the performance. Unit of refrigeration. 1 ton of refrigeration is defined as refrigerating effect produced by melting of 1 ton of ice from and 0 degree centigrade in 24 hours is defined as a ton of refrigeration, which we have already discussed. Then the refrigeration capacity. This refrigeration capacity is the rate at which heat is being absorbed from the refrigerated chamber, and the refrigeration capacity is being expressed in tons of refrigeration. That is being expressed in terms of tons of refrigeration. As we have already known, the ton of refrigeration is being defined as 1 ton is nothing but 1000 kgs, 1 quintal is nothing but 100 kgs, 1 ton is nothing but 1000 kgs of water at 0 degree centigrade. To convert that, the same one as an ice at same 0 degree centigrade in 1 day. Okay, the 1 ton of refrigeration is also given by latent heat of ice into 1000 kilojoules per day, which is equals to latent heat of ice into 1000 divided by 24 kilojoules per hour. Because we have 24 hours in a day, I will divide it by 24, convert that kilojoules per day into kilojoules per hour. Now I will further reduce it to kilojoules per minute by multiplying by 60. Is that clear? If I multiply by once again 60, so I will get it in terms of kilojoules per second. So this is the actual value for any ton of refrigeration. This is how you have to calculate. So the latent heat of ice into 1000, so that will leads to 3.5 kilojoules per second of refrigeration capacity. So that is nothing but 1 ton of refrigeration is given by 3.5 kilojoules per second, or it is nothing but 210 kilojoules per minute. Then what do you mean by refrigerant? In a refrigerator system, a medium called refrigerant continuously extracts the heat from the space within the refrigerator, which is to be kept cool at the temperatures less than the atmosphere, and finally rejects to it some of the fluids like ammonia, freons, hydrofluorocarbons. No, actually we are not using CHFs, it's only because they are harmful to the ozone layer. So methyl chloride, carbon dioxide are the commonly used refrigerants. Okay. Then what are the different properties or good properties of a refrigerant? That means I cannot use all the liquids as a good refrigerants. What all a good properties it has to possess is nothing but a good refrigerant must have a low boiling temperature at atmospheric pressure, and a good refrigerant must have a very low freezing point, because the refrigerant should not freeze at low temperatures, in order to avoid the leakage of the atmospheric air and also to enable the detection of the leakage of the refrigerant. Both the evaporator and condenser pressures should be slightly above the atmospheric pressure. The latent heat of evaporation must be very high so that a minimum amount of refrigerant will accomplish the desired results. In other words, it increases the refrigeration effect. The specific volume of the refrigerant must be very low. The lower the specific volume of the refrigerant at the suction of the compressor reduces the size of the compressor. Different refrigerants. The first one, which is more popularly used, is an ammonia in a vapor absorption refrigeration system. Ammonia as a refrigerant is employed in a refrigerators operating on the absorption principles because of its high latent heat, which is of 1300 kilojoules per kg at -15 degrees centigrade, and low specific volume of 0.509 meter cube per kg. Okay, at -15 degrees centigrade. It produces high refrigeration effect even in small refrigerators. Since ammonia will not harm the ozone, it is environmentally friendly. It is widely used in cold storage, ice making plants, etc. And it is toxic, flammable, irritating, and food destroying properties makes it unsuitable for domestic refrigerators. Though it is not, it is a bit toxic, so that makes the ammonia to be not used in the domestic refrigeration systems. Is that clear? So then soon after that, if you take carbon dioxide is being used as one of the advanced refrigerant that can be used in the refrigeration systems because of its non-toxic, odorless and colorless, and it is non-flammable and non-corrosive in nature. Okay, next one is the sulfur dioxide, SO2. Earlier, sulfur dioxide was one of the most commonly used refrigerants in domestic refrigerators. Although it has got a better thermodynamic properties, it has a low refrigerating effect and high specific volume. Therefore, large capacity of high-speed compressors are required, since it combines with water and forms sulfurous and sulfuric acids, which are corrosive to metals, and they are highly concentrated in nature. That is why the refrigerators they are not preferred. The methyl chloride was used earlier in domestic and small-scale industries refrigerators, since it will burn under some conditions and slightly toxic, so it is not generally used. Freon is most popularly used domestic refrigerators. These refrigerants are colorless, almost odorless, non-toxic, non-inflammable, non-explosive, and non-corrosive. Freon 1,2 and Freon 2,2. There are some specifications here. They have given it. No need to go in deeper for that. Are the two Freon refrigerants commonly used in domestic refrigerators and air conditioners. Although these refrigerants are being now used extensively in the refrigerators, the air conditioners, it has been found that these refrigerants posing a major threat to the global environment through their role in the destruction of the ozone layer. This is what is the actual situation. The refrigeration system, there are two refrigeration systems are there. One is vapor compression and the other one is a vapor absorption refrigeration system. Now this is a vapor compression refrigeration system. Now basically what happens, this evaporator section will be exposed. If you have a refrigerator like this, if you open the door of a refrigerator, whatever the phase, what you see it here, this is nothing but an evaporator section. If you see the back side of a refrigerator, this is nothing but a condenser. You can see these coils, a black color, basically that will be made up of a black color one, and they will also be a grit will be there. Okay, now this black color pipeline pipes which have been shown at the back side of the refrigerator is a condenser, and the front side what you see when you open the door inside the refrigerator, it is nothing but evaporator. Compressor will be in a black color, that will be always kept at the bottom. Is it clear? so that maintain the vibrations and power consumption. Now at this position of 1, now let me start with this. At point 1, the refrigerant with the low temperature and low pressure liquid will enter into the throttle valve or an expansion valve. Low temperature and low pressure liquid will enter into over here, where this will be expanded to a very high, to the 4th position, where the refrigerant is of a higher temperature and now at this position it is 1, where it is of a very low temperature and very low pressure liquid refrigerant will enter into the evaporator chamber. In this evaporator chamber, what happens? Whatever the food that we keep it, whether it may be vegetables or it may be something medicines or whatever it may be, which will have some certain temperature, that heat will be taken away by this refrigerants. Then what happens? It becomes a low temperature and low pressure vapor. The liquid is entering here, low temperature, low pressure, and the same will be converted into vapor because it is absorbing the heat. Once it absorbs the heat, then what happens? Whatever the vegetables, fruits, medicine, what we have it there will be cooled. So because its heat is been taken away gradually. So the vapor, low pressure, low temperature will enter into the compressor, where it will be compressed to a very high pressure and temperature. So the very high pressure and very high temperature and pressure vapor refrigerant will go into the condenser, where the condenser will condense it into a lower liquid level, high temperature and high pressure liquid level. Is it clear? Then it will come out as in the 4th point, high temperature, high pressure liquid refrigerant will come out of the condenser. Then it will allow to flow through the throttle valve, which gives an effectively reduces the high pressure and high liquid, that is a high reduces it to low temperature and low pressure liquid. Is it clear? So further what happens? The same thing will circulate again and again. Whatever we are supplying the electricity or a power, it is for the compressor to operate and does the work. Let me go through it. Vapor compression refrigeration consists mainly of 4 components. One is evaporator or a refrigerator chamber, it is the same thing, compressor and condenser or a cooler, and a throttle valve or a pressure reducing valve or an expansion valve, or it may be the other any means which reduces the valve. A low pressure, low temperature liquid enters into the refrigerated chamber. It absorbs the heat in the chamber and changes its phase from liquid to the vapor. At the exit of the refrigerated chamber, we have a low pressure, low temperature vapor. This vapor is being taken by the compressor, which compresses it to a very high pressure and temperature. Due to high compression, the temperature of the vapor rises above that of the atmosphere. The high temperature, high pressure vapor passes through the condenser. It loses heat to the atmosphere and changes its phase from vapor to the liquid at the exit of the condenser. We have the high pressure liquid at moderate temperatures. The liquid passes through the throttle valve, where it suddenly expands at a low pressure. Thereby, the sudden decrease of the temperature due to decrease in the pressure. And at that inlet to the refrigerated chamber, we have a low pressure, low temperature liquid. Thus, the cycle is being completed. And this keeps continuously as it processes. Now, this is a vapor absorption refrigeration system. In this vapor absorption refrigeration system, we will have a liquid ammonia as a working fluid. Now here what happens? The ammonia and water has got a different boiling points. Ammonia and water has got a different boiling point. That is the idea we had of it. At position 1, a low temperature, low pressure ammonia will enter into the evaporator coil as usual. It absorbs the heat from the refrigerated place and it becomes a vapor. So at the position of 2, low temperature, low pressure vapor will comes out and then it will be mixed with an absorber. In the absorber, what happens? The ammonia will be mixed with a water. Is it clear? It will be mixed with the water. Then it will go to the this mixed absorber, that is the water. It is been mixed with the water. This mixed ammonia and water will be pumped through a heat exchanger. It will be pumped through the heat exchanger. No compressor over here. It will be pumped through the heat exchanger. It will send to the generator, where in the generator heating coils will be there. What happens? It will heat the mixture of, what is this, strong ammonia solution. Strong ammonia solution means it will have a water as well as the ammonia. It will enter there, and then it will be separated. What happens? The ammonia will be separated because the boiling temperatures are different. What happens? The ammonia will be separated. Thus the separated ammonia will be taken out through the section 3, where the high temperature high pressure vapor ammonia will enter into the condenser. Once the ammonia is being separated, the water is being left out. That water will go down through the expansion valve to the absorber bag. So this is what is happening. In the 5th position, what is happening? Strong ammonia with the water is going there. In the 6th, what is happening? The ammonia is separated and the weak ammonia is coming back to the absorber using a heat exchanger. Is that clear? So this is the one. Then obviously the high temperature high pressure vapor will be condensed to a high temperature high pressure liquid, and this liquid will be allowed to pass through the throttle valve, where it will be expanded, and this expanded one will be of lower temperature lower pressure liquid will enter into the vapor. This is what it just this is being carried out. In vapor absorption refrigeration system, we choose a combination of a refrigerant and a solvent. Solvent is nothing but a water anyhow, in such a way that the solvent absorbs large quantities of vapor refrigerant at low temperatures and gives off vapor when heated to higher temperatures. Ammonia and water are such a combination, where low pressure low temperature ammonia liquid enters into the evaporator chamber. It absorbs the latent heat in the evaporator coils and becomes vapor. The ammonia vapor, which is at low temperature, is absorbed in the water in the absorber. The pump pressurizes the ammonia solution and supplies into the generator. The solution is being heated, and the generator is nothing but a heating coils. Because of the different heating properties, ammonia will be separated and water will be sent backside, and ammonia will be sent to the condensers. The solution is heated in the generator and water gives off the ammonia vapor at high temperature and pressure. This vapor is condensed in the condenser by rejecting the heat to the atmosphere. Then as usual, the high pressure high temperature liquid is suddenly expanded in the throttle valve to a low pressure. Sudden drop in pressure results in drop in temperature of the liquid. Then the low pressure low temperature liquid ammonia enters the evaporator chamber, and the cycle is being repeated. In the heat exchanger, the pressurized strong ammonia solution passing from the pump to the generator recovers some amount of heat from the weak ammonia solution, which is passing from the generator to the absorber. A pressure reducing valve is provided between the heat exchanger and the absorber to reduce the pressure of the weak ammonia solution to that of evaporator pressure. This is the major working principle of vapor absorption refrigeration system. This figure will give you a clear picture of how this domestic refrigerator is being used. Now, as you can see, this refrigerator cabinet is nothing but whatever we keep our all food. It is nothing but the cabinet. If you open that, there will be one white color plate. Basically, behind that plate itself, we will have an evaporator coils. The domestic refrigerator is one found in almost all the homes for storing food, vegetables, fruits, beverages, and much more. The figure shows different parts of a domestic refrigerator. It is more or less the same thing. Refrigerant will be there, compressor will be there, condenser will be there, expansion valve or a capillary tube, and then the evaporator or chiller or a freezer will be used. If you see this capillary tube, which is being placed through which the temperature will be reduced around, see, in the capillary tube the temperature will be around 7 degrees centigrade while at the entry. While at the exit of this capillary tube it will be minus 25 degrees centigrade. So minus 25 degrees centigrade means even it will get evaporates even at 0 degrees centigrade also. So that is the reason why we will feel that our fruits and vegetables so cold. It absorbs that complete heat. Is it clear? So evaporator freezer at minus 15 degrees centigrade. Is it clear? So it absorbs and then it comes back once again to the compressor. Then it will go to the air which is outside, which is being exposed to. It gives away heat at 55 degrees centigrade. And then the air which gives away the heat. That is the reason why even if you put your hands behind the refrigerator, you always feel it is hot. Is it clear? The difference, the last concept here, it is nothing but difference between a VAR and VCR, vapor absorption refrigeration system and vapor compression refrigeration system. In the vapor absorption refrigeration system uses low grade energy like heat, therefore may be worked on exhaust systems from IC engines. Whereas in the vapor compression refrigeration system it uses high grade energy like mechanical heat from the compressor, whereas here a pump is being used, no compressor, it is a pump will be used. Moving parts are only in the pump, which is a small element of the pump system, hence operations is smooth. Whereas here the compressor is being used, therefore more wear, tear and noise may occur. Is it clear? The system can work on lower evaporator pressures also without affecting the coefficient of performance. Whereas here vapor compression refrigeration system, the COP decreases considerably with the decrease in the evaporator pressure. As we decrease the evaporator pressure, the COP also decreases. Is it clear? Now, no effect here in the actually VAR, there are no effect of reducing the load on the performance. Performance is adversely affected at partial loads. It is only because the compressor is being used in this vapor compression refrigeration systems. Liquid traces of refrigerant present in the piping at the exit of the evaporator. It will be there because the ammonia is being mixed with a solvent, or it may be a water. Liquid traces in suction line may damage the compressors. Automatic compression of controlling the capacity is easy and it is difficult over here. Charging of refrigerant is simple and it is cheap, whereas the charging of a refrigerant is difficult. Part load performance is low, whereas the no effect of refrigeration of the load will be considered over here. That means actually what happens here, when you talk about the vapor absorption refrigeration systems, since it will be allowed to mix with a solvent and a heat, that is the thermodynamics will be used, the low grade energy will be used. So the efficiency is more. Though the efficiency of a vapor absorption system is more, it is not used because of its toxicity and odor that it produces. In most of the high-end applications, if you go for any big malls where the meat has to be stored, say for example in the hospitals where the dead bodies has to be preserved, in such kind of cases the vapor absorption refrigeration systems are used for a larger capacity. Only for lower capacities like household applications, vapor compression refrigeration systems are used. And nowadays even this vapor compression refrigeration systems are not preferred because the refrigerants which are used in this VCR is damaging the ozone layer. So that is of major concern. Okay. Now this ends the refrigeration system in the 6th session of the 3rd module, and we have left out with only the air conditioning system. Let us discuss in the next class.